So hey guys, this is Dipesh, and in this particular video we'll implement image classification using a convolutional neural network, and specifically we will try to use the LeNet-Phi architecture of CNN. Okay, so the first thing that we have to do is which we do in all our videos, that we have to download the dataset. Now the dataset that we'll be using for image classification is called as MNIST dataset. It is basically a dataset of handwritten digit images. So let me just show you some examples. So if I write MNIST and search on Google, and let's see the images. So you can see that each image here is basically a 28 by 28 image. Okay, so basically these are grayscale images, and we know that grayscale images have only one single channel. Okay, so the size of each image would be 28 by 28 by 1. Okay, so you can see the these are how the images in MNIST dataset will look. Okay, so we'll not download any external download these images externally. So in Keras already provides a bunch of inbuilt dataset, and one of the inbuilt dataset that Keras provides us is called as MNIST. Okay, so what we'll do is, let me just create some more cells. Okay, so the first thing that we'll do is we'll first import our necessary libraries. So we'll import NumPy, then we'll import matplotlib, so that we can plot so that we can view our images. Okay, and the next thing that we'll import is Keras. Okay, so I'll write from Keras dot datasets import MNIST. Okay, so the MNIST function that Keras provides, it automatically basically loads the entire dataset. So if it's not already downloaded, then it will download from the internet. Okay, alright, so also let's connect our runtime. Okay, just click on your runtime and see if your runtime is GPU or not. If not GPU, then just select the GPU option. Okay, and let's connect it. This is basically, I'm using the Google Colab. Okay, we use the same tool in our previous video. Okay, so if you don't know what Google Colab is, just watch the video again. It's a very powerful tool, and it's a very useful tool. Alright, so now let's run it. Alright, so now what we'll do is we'll load our dataset. So the MNIST function basically returns the splitted dataset. Okay, so basically it automatically splits the data for us, so we don't have to use the train test split method anymore. So what it returns is, it will return X train, and it will return Y train, and again it will return X test, and it will return Y test. Okay, and then what we'll do is we'll do MNIST dot load data. Okay, so yeah, this is what it returns. Let me also put a comma here. Okay, now let's run it, and then I will show you how to plot the images. Okay, so now you can see that it has downloaded the data set. Okay, this is basically the API that it used. Once it is downloaded, then if you try to use it again, it won't download the dataset from the internet again. It will use the dataset which has already been downloaded. Okay, now let's plot some images. Okay, so what I will do is I'll write for I in a range phi. So we'll plot 5 images, and we'll do plt dot imshow, and we'll pass one image from our training image. So I'll write I, and I'll also mention the C map. Okay, since our image is basically grayscale, we'll pass it the gray option, gray value. Okay, then what we have to do is we have to do plt dot show. Alright, let's run it and see how the images look. Okay, so you can see these are our images. So basically it provides two things. First, the X train will contain these images, okay, and the Y train will basically contain their labels. So this is, so for example, this is the image of 0. Then now Y will consist of the label as 0. So let me also print some Y values so that we can see how it looks. So I'll write Y train and let's print it. Okay, so you can see that our first value is 0 and our second value is first value is basically of 5 and second value is 0. So you can see our first image is 5 and our second image is 0. So this is how basically the data set is. Alright, so since each of this label represents only one number, what we'll do is we'll apply one hot encoding here. So what we want is, we want for each image, for example, if this is 5, then we want 10 probabilities. Okay, so we want 10 probabilities indicating which number it is. So for example, if we give our model, for example, the image of 4, okay, if we give our model this image, then what we want is, we want our model to output 10 probabilities. So it should be something like that: 0 0.2, 0 0.3, 0 0.6, 0 0.9, you know. In this way we want 10 probabilities, and since our input value, let's say, is 4, then the highest probability should be at the 4th position. See, 0.9, that is 90%. So what we'll do is, for each label we'll get 10 probabilities for where each probability belongs to each class, okay, each number. And this, in this way, basically we'll create our model, so that whenever we input an image, it will give us 10 probabilities, and by looking at that probabilities, we will get to know, we'll see how, which number it is, okay, which image it is. Okay, so the first thing that we have to do is, we have to since we have only one value, we have only one label for each image, what we'll do is, we want one array, okay. Basically we want to basically encode each label, so that each sample has 10 probability values, okay. So let's do it, and then we'll see how it looks, okay. So what I'll do is, I'll write converting labels to probabilities. Basically, it is, in simple words, it is just one hot encoding, okay. So what I will do is, I will write our new Y would be this. Let me just copy and paste to save some time. Okay, so you see here we have also let's not use the entire data set, okay. Let's not use the entire data set. So what we'll do is our X would be, let's take only the first 100 images, okay, because this dataset consists somewhere around 40 to 60,000 images, and in order if we try to train all of them, and then it would take a lot of time, okay. So just so in this video I'll just train 100 images. On your system, what you can do is, you can use the entire dataset. So what I'll do is, I'll use the first 100 images as our X, and our Y would be the first 100 labels, okay. So I'm using only the first 100 images. So let's run it. Let me remove this, okay. So I will use only 100 images, and now what I will do is, let's split the data set, okay. Let's split the data set manually. This is only, I'm only doing this because I don't want to use the entire data set. It will take like 10 to 15 minutes to just train the model. So in order to save the time, what I'll do is, I will just use 100 images. So let's split the data. So what I will do is, I'll do from sklearn dot model selection import train test split, okay. And train test split basically returns 4 values. It will X train, it will return x test, then it will return y train, and then it will return y test. And let's call this function train test split, and it will take our x and it will take our y, and it will take the test size. So we'll follow a 70-30 rule. So we'll use 70% of the data, that is 70 images for training and 30 images for testing. So I'll write 0.3, which indicates 30. Okay, let's run this. Oh, okay. So also let's run this one this before splitting the dataset. So what I will do is I will add this before splitting the dataset. So now let's run everything again. Okay, let's run everything again. Okay, so what we did was we called the MNIST dataset, and we loaded the dataset. We plotted some images, and then we basically used only 100 images. We just took only the first 100 images. Okay, and then after that what we did was we converted our y basically to have probability values. So basically we applied one hot encoding to each label. Okay, so now let's print the label. Let's see how the y labels look. So what I will do is I will do print y encoded. Okay, okay, so now you can see that previously we are having only one label. Okay, one label for each image. So now we have basically an array. Okay, so now we have, for each image we have 10 probabilities. We have, you can see we have 10 basically we just applied one hot encoding here. Okay, so we know that the first image is 5. So you can see that at fifth position of our first label y value, you can see that the fifth position is 1 and rest all is 0. So we did the same thing for all the images. Okay, and after that we basically split our data set. Okay, alright, so the next thing we have to do is we have to reshape our y. Okay, we have to reshape our x basically. Okay, so let's reshape our x. So now what reshaping means is basically whenever you will pass images to the images to any convolutional layer in Keras or TensorFlow, what you have to do is you have to reshape them to a common format. Okay, so now the format that TensorFlow uses is something like this. So we have to reshape our dataset to something of this dimension. So it will take number of images, width, height, and then channels. Okay, so this is basically the dimensions that the API wants. Okay, this is the dimensions that the TensorFlow takes. So if we have, let's say, 100 images of 28 by 28 by 1 size, then what the dimension would be? It would be something like this: 100, 28, 28 by 1. Okay, this would be our dimension. So let's see what is the current size shape of our data set. So we'll print xtrain dot shape. So let's see. So as of now you can see this is our size is basically 70 by 28 by 28. So we also want the channels here. Okay, so what we'll do is we'll just reshape both xtrain and xy. So we'll write xtrain is equal to xtrain dot reshape, and what we'll do is I'll write xtrain dot shape and get the number of images in xtrain. And then what we'll do is we know that our image height and width is 28 by 28 and the channel is 1, so we'll just pass 1, and we'll do the same thing for our test dataset. So I'll just do this. I'll just write x test, and also let's do here x test, and again let's do here x test. Okay, so now let's run it. Alright, so now let's again print the value. Okay, xtrain dot shape. Now you see that the shape of our dataset is in this format. Okay, so remember, whenever you will be dealing with convolutional neural nets, you have to before passing this dataset to the model for training, you have to bring the dataset in this format. Okay, now I know this would be very confusing at the beginning, but the more you practice, the better it would be. So at the beginning, the only difficulty while using convolutional neural network is understanding this shapes and different size of different dimensions of arrays and matrices. Okay, so just don't worry. Whenever you will be dealing with images, just try to bring all the entire dataset in this format. Now for PyTorch may not use this. If you're using PyTorch library, then PyTorch may have some other different format for this. So you have to basically check the format that you have to reshape your dataset before giving to a model. But for Keras and TensorFlow, this is the only format that we use. Alright, so now our data pre-processing is complete. Now what we have to do is we have to create our model. So what I will do is I will write model creation, and I will let's import some important functions. So I'll write from keras dot models import sequential. Sequential is basically a function in which we add the layers of our neural network one by one. Okay, and next what we'll do is we'll import the layers that we want to add to our model. So I'll write keras.layers.import, and I'll write con2d con2d, and the next thing that we will add is we'll add a dense layer. Okay, basically a fully connected layer, and then we'll add flatten. Okay, flatten is basically used at the end of the convolutional layer, at the end of the final convolutional layer, so that we basically just reshape the entire feature maps to just have to a single big array, and that basically then becomes the input to our next dense layer. Okay, and next we have to import the average pooling layer. Okay, we are using average pooling 2D, but if you want, you can also use max pooling layer. So it totally depends upon you. So if there are basically two types of pooling. Okay, one is average pooling and max pooling. So depending upon what you want to use, you can choose any other. You can import any function you want. So I'm using average pooling here since we discussed average pooling in our convolutional neural network video. Okay, so now we have imported our library important functions. So now let's create the model. So what I will do is I will write model is equal to sequential, and I will do model, and then I will do model dot add. So the first layer, if you look, so what we are trying to create here is we are trying to create the LeNet architecture. So if I search LeNet 5, and if we just look at some images, so here you can see that we have two convolutional layers and we have two pooling layers. So we'll do the same thing in our network. So the first thing that I will do is I'll write con2d. Okay, and con2d basically takes multiple important arguments. The first is the number of kernels or filters. So we'll use 6 filters. All right, and then it takes the kernel size. Okay, kernel size is basically the size of the kernel that it will use, size of the filter or the kernel that it will use while performing the convolutional operation. Okay, so the kernel size will use 3 by 3. Okay, and the next argument that it takes is it takes activation function. So activation function is applied after convolutional operation. Okay, so the activation function that we'll use is called as something called as hyperbolic tangent. So hyperbolic tangent, it's also called as tan edge. It's a very simple function. All it does is it takes a value and it converts those values into a range of -1 to 1, -1 to +1. Okay, so the formula of this function is very simple. Just look at the Google, go and look on Google. Just type hyperbolic tangent. So let's do this, hyperbolic tangent. So if I look at the images here, so here you can see this is the formula. Okay, this is the formula. So it's a very simple formula, 1 upon e raised to -2x upon 1 plus e raised to -2x, and this is the curve. So it converts all the values in the range of -1 to 1. Basically the S curve is similar to sigmoid. Alright, so the next thing that we'll do is we'll mention the input shape. Okay, we'll mention the input shape. Input shape is nothing but what would be the size of our size of one image. So our size of one image is 28 by 28 by 1. Okay, now this input shape argument is only given is only mentioned in the first layer of a neural network. Okay, so we don't have to mention the input shape in the upcoming layers. So next thing what I'll do is I'll do model dot add, and I'll write average pooling 2D. Alright, and average pooling 2D will not take any special arguments or anything. Okay, just keep it as it is. Okay, so let's just copy this entire thing. Okay, and let's just paste it. Okay, let's remove the input function, input shape argument. Okay, and let's increase the number of kernels to 12. Okay, so after applying convolutional operation here, we'll have 12 feature maps, and also let's keep the kernel size as it is. Okay, so according to LeNet, the LeNet architecture has 2 convolutional layer, and it has one or two dense layer. So next we'll try to add the dense layer. Okay, so but before adding a dense layer, what we have to do is we have to add a flatten layer. Okay, we have to add a flatten layer. So what flatten layer does is it just converts all the feature maps. Basically the feature maps will have 3-dimensional values. Okay, basically the shape of the feature maps would be something like height, width, and the number of channels, or something like this in 3 dimensions. Okay, so it will convert all these 3 dimension feature maps, basically a stack of feature maps, into a single array. Okay, into a single big array, and that array would be basically the input layer to the next fully connected layers. So what we'll do is we'll add 2 dense layers. Okay, we'll add model dot add dense, and it will take the number of nodes in the hidden layer. Okay, so let's keep it to 50, and the activation function that we'll use would be tan h again. Okay, would be tan h. Alright, now let's copy this and let's paste it. And since we want 10 probability values for each image that we input, the output layer will contain 10 nodes. Okay, and since we want probabilities, we'll use the softmax function. Okay, softmax function basically takes an array, okay, an array or list of numerical values, and then outputs another array of the same size, but it will contain probabilities. Basically it is it is the extension of sigmoid function. So sigmoid function just takes a single numerical value, a single number, and gives out a probability. But software function takes multiple values, a list of values, and then basically outputs a list of probabilities. Next, what we'll do is we'll print the summary of this model. So printing the summary will basically print the number of print the number of learnable parameters, and also print some other useful things. So it's taking its time. Okay, so now you can see this is basically a summary of the input. So you can see the input shape, you can see the input shapes of our images here. So you can see the output of our first convolutional layer would be a 26 by 26 by 6 for shape. Okay, so now you can see that what happened here is after the final average pooling layer, what happened is all these values got converted into a single array. So if you okay, so after once the once the values have been flattened, this flattened layer our flattened layer basically becomes the input layer to the next dense layer. Okay, and finally we get 10 probability values as output. So the next thing that, and you can also see we have 16,000 learnable parameters. Okay, so we have more than 16,000 weight values to learn. So let's now train our model. Train the model, and training the model is very simple. All we have to do is we just have to apply two functions. So we'll do model.compile. Okay, and the next is model.fit. Okay, now let's pass the necessary arguments to each of this function. So the compile function will basically take two important things. First is the loss. Okay, loss, and the loss that we'll use here is we'll use a type of cross entropy called as sparse categorical entropy. Okay, so let me just paste the whole name here. Okay, so you can see this is basically a type of loss function. Okay, it is used when you have lots of zeros and ones in your output. So here you can see we have lots of zeros and zeros in our in each of our output. So this is basically a sparse matrix. That's why we use something this sparse categorical and cross entropy. It's also okay to use any other loss function, it will work, but sparse categorical entropy will basically give us a much better accuracy as compared to other loss function in this case. Next we have to give it the matrix that we want to print during training. So we'll pass it as accuracy. Okay, so we want to see what is the accuracy of our model. And the fit method will basically take two things. It will take our x train and it will take our y train, and it will take the number of epochs. Okay, so okay, now let's train this. Now you can see that the model has started training. Okay, and all the details will be shown here. Let's just wait some more time. Okay, the compile function also takes many other useful parameters, like the type of optimizer and also many other things, but at this stage it's okay. These two we don't have to get into more details. Alright, so here you can see that for 10 epochs our loss basically got reduced and our accuracy was increasing. So at the final stage we got 0.9 accuracy on our training data set. Okay, now let's see what is the accuracy of our model on our test data set. So I'll do model dot evaluate, and I will pass our x test and I will pass our y test. Okay, and then I will print the score. Okay, I'll print the score. Okay, let's run it. Okay, so here you can see we are getting 76% accuracy on our test date. Now remember, we are using only 100 images here. Okay, I'm not we are not using the using the entire data set. The entire data set consists of somewhere around 50 to 60,000 images. Okay, I'm only demonstrating how to basically go about creating the model. Okay, on your system you can train this model on full data set. Okay, so now our model has been trained. Now what we'll do is we'll try to let's see if the model correctly predicts the function. So what I'll do is I'll write running inference, and we'll pass an image to the to the model and see if it predicts the image accurately. So what I'll do is I'll write firstly let's view the image ourselves so that we can confirm it visually. So I'll write plt dot I'm show, and I will pass it an image from our test data set. Let's pick an image at fifth index, and also let's reshape it. Okay, let's reshape it to its normal shape. So the normal shape is 28 by 28. All right, and the color map is gray since it's a grayscale image. Okay, now let's do plt dot show. Remember, the reason why I reshaped here is because we basically reshaped the entire X dataset to have the shape in this format. Okay, that's why in order to plot the image, I have to again reshape it back to its normal size. So let's run it. Okay, so here you can see the value at fifth index is 0. Okay, now let's give this image to our model. So what I will do is I'll do result is equal to model dot predict, and I will give our model x train. Okay, x test at an image at fifth index, and then I will print the result. Let's see how it works. Okay, we got an error. So what is it saying? Okay, I just forget this array. I just made a mistake in this array. Okay, what is it saying again? Okay, let me check it again. Let's do this again. Okay, let's do this again. What I will do is I will try this again. Okay, I will do model dot predict. Let's try and let's see if we get any other error. Okay, I will do x test, and then I will pass it the fifth index. Okay, okay, what error are we getting? Let's try removing this values. Let's try removing the brackets. Okay, again it's giving us this so what I'll do is I'll just copy a value, and let's see if this value basically gives us some error. So I'll do it as fifth index, and I will try to okay, so why did we not get an error here? Let's try removing the reshape function. Okay, so there is something with the with the reshape function here, I think. Alright, let's just copy this value, okay, and let's just try running predicting our image using this thing. Okay, so what we did here is we are doing model dot predict, and we are again reshaping this image, reshaping our image at fifth index in our test dataset to have to have only to have this shape. So why we are passing this shape is because since we are passing only one image to our model, uh, and the format that the model.predicts takes is this one. Okay, it takes number of images with height and channels. So since we are passing only one image, we are passing it as one, which indicates one image, by 28 by 28 by 1, which indicates the height, width, and the channel. All right, so let's run this and let's print the result again. Okay, let's print the result again. It's very confusing at the start because the model itself is not very difficult. The difficult part is understanding this shapes and all. Okay, so now you can see the model has given us 10 probability values, and we know that the image is of 0, so the highest probability is at first position, which indicates 0. Okay, so you can see for each position, for 1, 2, 3, 4, at each position the model has given probability, but the highest probability value, that is 0.6, which indicates 60%, is at 0 position. So let's try using some other image. So let's try an image at 9th position. Let's run it again. Okay, so the image at 9th position in our test data is 6. Okay, so let's see if the model predicts it. Okay, so you can see at 6th position, so we'll start at 0, 1, 2, 3, 4, 5, 6. Okay, so we didn't pass 9 here. Let's pass the 9th index here and let's run it again. Okay, let's run it again. Okay, so now you can see at the 6th position, so we'll start at 0, 1, 2, 3, 4, 5, 6. So at 6th position, we are getting the highest probability, that is the 50%. Okay, 0.56, which is 56%. So now rather than viewing the probabilities, so in order to view just the number, what we'll do is I will print directly the index. Okay, the index that at which we are getting the highest probability. So I'll do numpy dot argmax. Okay, and I will just pass the result value. Okay, and now what it will do is it will just print the label. Okay, it will just print the index with the highest probability. So now we see the model has predicted that the image has 6. Okay, now let's try some other image. So let's try it at 12th position. So let's run it. So you can see the image at 12th position is again, I think it's 0. Let's try some other, because we tried 0. Let's try at 15th position. Okay, again 6. We have already tried this 6th image. Let's try something else. Okay, let's try some other image. Let's try at 3rd position. Okay, so the 3rd position we are getting I think it's 7 or it's 2. Let's give this model let's give this image to a model and let's see what it predicts. So let's pass the 3rd index. Okay, let's see what it predicts. So the model has predicted it as 7. So you see, this is how we basically train an image classifier model. Now here we have only one channel. Okay, these are basically purely 2-dimensional images, but we mostly train CNN models on colored images. Okay, so the colored images are 3-dimensional images with 3 channels. So in our upcoming videos, what we'll do is we'll try to train image classifiers on colored images. Okay, but the topic of our next video would be something else. So we'll discuss a new type of neural network called as recurrent neural network. Okay, so yeah, see you in the next video.